Hello everyone, welcome to the 50th lecture in the NPTEL course on Riemannian geometry. So remember we were investigating this question of suppose you are given a geodesic, till what time does it keep minimizing the length. So till what is the maximal time till which it's a minimal geodesic. So in connection to that, so let us say we fix a unit tangent vector and we take the corresponding geodesic in that direction. Then we define the cut time t theta to be the supremum of all times t, so that gamma is minimizing on the interval 0 to t. Okay. So we obviously know that t theta is strictly bigger than 0, because in a geodesic normal neighborhood these radial geodesics will minimize at least for a short time. So the point is, how do we get a characterization for this cut time t theta. So let us say we have some t naught, so that q is equal to gamma of t naught. Then we had this important proposition that this t naught is actually the cut time. Suppose t naught is the cut time, then we have the following two possibilities: either q is a conjugate point, or you have another geodesic sigma which connects p to q. Okay, so the only way that your gamma can stop minimizing is if these two conditions hold: either you encounter a conjugate point, or you encounter a point where two geodesics come together. So in terms of the exponential map, this corresponds to singular values of the exponential map. So that means where the derivative of the exponential map is not injective. On the other hand, the criteria B is where the exponential map is non-injective. Okay. So that means you have two geodesics that come together at a point. And conversely, suppose A or B hold, then the cut time has to lie before t naught. Okay. So this was the important characterization of the cut point. Okay. So so today I want to use this analysis to basically give you essentially the maximal domain on which the normal coordinates, the geodesic normal coordinates, are defined. So here is a definition. So let again we as usual fix a point P, and as usual Mg is complete, right. I am not going to keep repeating this, but we are only looking at complete manifolds for now, actually for the rest of the course. Okay, so then we define the segment domain in the tangent space by the following. So it is denoted by dp tilde. So this is basically the union over all unit tangent vectors of t times theta, where t is strictly smaller than t theta. Okay. Then we define the segment domain in the manifold as simply the image of the exponential map, the image of dp tilde under the exponential map. Okay. Then we define the cut locus of P in the tangent space as simply the boundary of dp tilde. So Cp tilde is basically the union of this of t theta times theta. So this is simply the boundary of the topological boundary of dp tilde, and the cut locus in the manifold as the image under the exponential map of Cp tilde. Okay. So here is the key proposition. So firstly, this cut locus is a closed subset of M. Okay. Second, if you look at the segment domain in M, that's precisely the complement of the cut locus. Moreover, dp is dense, and of course it's also open because, and of course open by the first part, okay, because Cp is closed. The third point is that the exponential map between the two segment domains is actually a diffeo. Okay. So in other words, we have geodesic normal coordinates on this large open dense subset. Okay. And the fourth point is that for all x in dp, there exists a unique minimal geodesic which I will denote by gamma x from 0 Lx to m, such that gamma x of 0 is p, gamma x of Lx is x, and Lx is precisely the distance from p to x. Okay, so in other words, this is a unit speed minimal geodesic. Okay, so the proof of the proposition follows the following lemma. So the key lemma is the following, that a point q belongs to the cut locus if and only if either there exists a unit speed, so either q belongs to the conjugate locus of p along some gamma for some minimal geodesic from p to q, or okay, or there exists at least two minimal geodesics to let us say unit speed, so that you can't reparameterize, unit speed geodesic sigma gamma from p to q. Okay. So I will leave the proof as an exercise because the proof uses the characterization of the cut point from the previous lecture. So again, this is a good exercise to try to use that to prove this lemma. Okay. So I am going to to let you work that out, and this is a highly recommended exercise in order for you to make sure that you really understand what is happening with these cut times and so on. So let me move straight to proving the proposition. Okay, so I have to show that the first part is that I have to show that the cut locus is closed. So let Qk belong to the cut locus, and let us say Qk's converge to Q, let us say Q infinity. What is the goal? The goal is to show that Q infinity is also a cut point, right? That is what being closed means, that it contains all its limit points. So let Lk be the distance from P to Qk, alright. Then this of course converges to L infinity, which is the distance from P to Q infinity. Okay. Now after passing to a subsequence, because Qk's are points in the cut locus, by this lemma either A should hold or B should hold. Now you have a sequence and you have two options, they either fall into option A or fall into option B. So that means that I can pass to a subsequence, so that along that subsequence all points are either satisfy A or all points satisfy B. Okay. So I will just continue to denote the subsequence by the same index. So after passing to a subsequence, so instead of writing K subscript J, I will just use the index K. For all K, either there exists a theta k in the unit tangent sphere such that Qk is exponential of Lk theta k, gamma is the corresponding geodesic, right. So and this is a conjugate point, so that means that the derivative of the exponential map at Lk theta k has a non-trivial kernel. Okay, so that means that Qk is a conjugate point along the corresponding radial geodesic, or for all k the second possibility holds, that that there exists a sigma k which is right. So maybe let me rephrase this. Right. So there exists a theta k such that Qk is the exponential of Lk theta k, and the kernel of the derivative of the exponential map at Lk theta k is non-trivial. Okay. Or there exists another sigma k which is not equal to gamma k, where gamma k is just given by the exponential of, let us say, t times theta k, such that sigma k of 0 is p and sigma k of Lk is this Qk. Okay. So let us analyze the two cases. So case 1, suppose A holds. Okay. So passing to a subsequence, which I will again continue to denote by k, theta case by the Bolzano-Weierstrass property again converge to some theta infinity. Okay. But then if you take gamma infinity, is a minimal geodesic from P to Q infinity, right. Why is it minimal? Because its length is I mean, if you take gamma infinity of L infinity, that will be Q infinity, right, and L infinity is the distance from P to Q infinity. Okay, so so now for all k, because A holds, for all k there exists a Wk which is non-zero and in the kernel of the exponential map. So it is in the kernel of the exponential map at this point Lk theta k. Okay. So again by the Bolzano-Weierstrass property, if we normalize so that the norm of Wk is 1, which one can always do, the kernel is a vector space, right. So one can always normalize so that this is norm 1. Then these Wk's will also converge to some W infinity after passing to a subsequence. Okay. But then by the continuity of the derivative of the exponential map, because the exponential map is a smooth map, right, we basically get that the derivative of the exponential map at the point L infinity theta infinity acting on W infinity is also 0. Okay. And W infinity cannot be 0 because it has norm 1. Okay. So this implies that that the kernel of is non-trivial, which implies that that Q infinity, which is the exponential of L infinity theta infinity, is a conjugate point to P along gamma infinity, which in particular implies by our lemma again that Q infinity is also a cut point. Okay, so in this case we have shown that Q infinity is a cut point. What about the second case? Suppose B holds. Then let sigma k of t be equal to exponential of t times Vk, where Vk is some unit tangent vector. So again by the Bolzano-Weierstrass argument, after passing to a subsequence, Vk converges to V infinity and these theta k's converge to theta infinity. Okay. So again, like before in the proof of this proposition from last time, we have two cases. So case 2a is that that this V infinity is equal to theta infinity, and the second case where this. So arguing as before, I am not going to repeat the argument as in the previous lecture. I am not going to repeat the argument. Case 2a implies that that in fact Q is a conjugate point. So along this limiting geodesic gamma infinity. Gamma infinity is the geodesic with initial vector in the direction of theta infinity. And similarly, case 2b implies that there exists two minimal geodesics, sigma infinity given by the exponential of t times v infinity and gamma infinity given by the exponential of t theta infinity connecting p and q infinity. So, in either case we see that q infinity is a cut point by the lemma. Okay. So, that completes the proof of the first part. So cut locus is closed. Okay, what about the second part? So, for the second part, clearly the complement of the cut locus is obviously contained in this, right, because there is a minimal geodesic, there is a unique minimal geodesic from P to any point in the complement, and hence that has to belong to this segment domain. Okay, so for the reverse inclusion, I have the following claim. That the exponential map from the segment domain in the tangent space to the segment domain in M is injective. Okay, assuming this, let us prove the reverse inclusion. So, assuming this, let Q belong to dP, then there exists a unique theta. This comes from the injectivity that is being claimed in that has been claimed earlier, such that Q is the exponential of L theta, where L is just the distance from P to Q. Okay. So, also by the definition of dP tilde, if so by definition of dP tilde, it was basically the union of all time all vectors t times theta, where t is strictly smaller than the cut time, right. So that means you can find a little epsilon, so that t plus epsilon is also less than the cut time. So there exists an epsilon such that L plus epsilon times theta is also here. Okay. So this implies that gamma given by the exponential of t theta is actually minimizing on the interval 0 to L plus epsilon, which means that Q cannot be a conjugate point. Okay. And in fact, this is sort of the unique geodesic connecting P to Q, because we are working only on the segment domain, and the exponential map is injective there. Also, there does not exist another minimal geodesic from P to Q. So this together implies that Q is actually in the cut locus. Sorry, this implies that Q cannot be in the cut locus, because it can't satisfy either this property A or the property B. in the lemma, right. So, q cannot be in the cut locus, which means that q is in the complement of the cut locus. Okay, so this in particular implies the reverse inclusion, and we are done. Also note that that this implies that dp is clearly open. So, I now claim that this is also dense. Okay. What is the proof of that? So, indeed let q be in the complement of dp, but of course we know that the complement of dp is simply the cut locus, right. So, then there exists a unit tangent vector such that q is the exponential of the cut time times theta. Then just take qk to be the exponential of t theta minus 1 by k acting on theta. So, each of these qk's will now belong to the segment domain, and clearly qk converges to q, which implies that q is in the closure of dp of the segment domain dp. So, we have shown that any point in the complement lies at least in the closure. This means that this is all of M, or that dp is dense. Alright, how do you prove the third part? Well, we already from right, sorry, I'm still I have to prove the claim. Okay. So, so we have to show that this is actually injective. So, remember what was the claim? We have to show that that this is injective, but that's easy, because if it were not injective, then there exists two vectors, let us say VW in or theta and V in okay, and some L such that the exponential of L times theta okay. Why do we have a L, why do not we have an L theta here and some L prime V? Because since these points belong to the segment domain, the geodesic up to that point is minimizing, right. So, that means that the distance of those I mean of that point will basically just be L. So, you have some L, so that exponential of L theta is the same as exponential of LV, but then you basically have two geodesics coming together, right. So, this would imply that that the point Q is in the cut locus, which would imply that which would be a contradiction, right. So, this would be a contradiction. Okay, so, the exponential map is injective on this domain. Okay, the third point was that the exponential map from dp tilde to dp is a diffeomorphism, but we have already seen that this is bijective from the previous claim, right. So all that needs to be done is to prove the following claim, that for all v in dp tilde, the derivative of the exponential map at v has trivial kernel, because then we are done by the inverse function theorem, xp is a local diffeo but it is a global bijective map so this implies it is a diffeo. Okay. So it's enough to prove the claim. Okay, so suppose there exists a W not equal to 0 belonging to the kernel of this map. Okay. But then this implies that that if you consider gamma t to be the exponential of TV, then gamma of 1 is conjugate to P along gamma, okay, which implies that gamma of 1 will have to belong to the Cut-Locus, but that's a contradiction. Right, since gamma of 1 belongs to dp, and this is obviously phi. In fact, dp is the complement of the Cut-Locus. Okay. All right. So actually, sorry, I need to be a bit careful. So right, but the point is that that gamma, because v belongs to dp tilde, gamma is actually minimizing on this on a slightly larger interval by the definition of dp tilde, right. But then gamma of 1 cannot be a conjugate point by our index theorem. So this is a contradiction. Okay, so this proves the claim. And the fourth part is an easy consequence of 2, right. And the lemma. So the lemma says that you can't if you take an x in the complement of the Cut-Locus, you cannot have two geodesics coming together, right. So then there is a minimal a unique minimal unit speed geodesic connecting these 2 points. Okay, so the final thing I want to do in this lecture is to state the following corollary. So let rho of x be the distance from P to x. Then it turns out that rho restricted to the segment domain minus the point P is actually a smooth function. So the distance function is smooth, and moreover the gradient of rho is simply given by this unique unit speed minimal geodesic connecting P to X, the derivative at Lx. Okay, so how do you prove this? Well, so we have normal geodesic normal coordinates on dp. Say you label the geodesic normal coordinates by x1 to xn. Then we have seen earlier that radial geodesics basically minimize distance. So then this distance function rho of x is simply this function rp that I defined earlier, which is basically just the Euclidean distance in the geodesic normal coordinates. So clearly this is smooth. So if you look at the right hand side, that's smooth everywhere except when all x1 up to xn are 0, which means that this is clearly smooth on all of dp minus the point P. Also, then the gradient of rho is just going to be the gradient of Rp, but we have seen that the gradient of Rp by an application of Gauss lemma was just del by del Rp, okay. But the radial derivative, again we have seen this before, is simply the derivative of this radial geodesic, right. So that completes the proof of the corollary. Alright, so that is it for this lecture. So starting for the, so we basically have now 10 lectures remaining. In the final 10 lectures, I am going to talk about the relationship between curvature and topology, right. So I am going to prove a couple of theorems which tell you that if the curvature satisfies some condition, then the topology or the smooth structure is highly constrained. Okay, so curvature affects the topology of your manifold. Alright, so that is going to be the theme for the last 10 lectures that will see us through to the end of this course. Alright, thank you for your attention and I will see you next time around.